Okay, so in the last sector for today, I'm going to discuss just a bunch of data sets and try to play with them and see what we get. Okay, so I won't have slides for them. I just do 1 hour and okay. The first data set is a lake data set. So if you go to the website, you should download this wblake.txt for the first one. Let's try and read it. Let's try and read it. So that's like a fish data set that you have. So this is from this. Let me just try and do it for you, and so you can look at it, just stare at the data for a little bit. The head of another one, right? You come down here and you say head of fish data. Okay. So you get this. So it's the age of the fish, length, and scale, right? So this is let me go to my PDF slide file. So what this does is this data set here is the length. So the whole thing is like a scale is different. Let me do this here. So this is the length data set at a certain age. Okay, so at an age, and it's for a fish. The fish is a small mouth. It's like a small mouth bass. It's like a bass type of fish. So it's a fish data set. Okay, and so this is a sort of a popular fish in North America, and they manage to sort of, you stock them, you have fishing regulations that you can't fish too much, and the whole population is maintained. So one tool is to study the population, is to understand the growth pattern of the fish. So the dependence of measures of size on like length on age and so on and so forth. That's what I'm trying to do. Okay? And how do you sort of a lot of people catch large fish, small fish at the same time, how do you manage it? Okay? So you understand how length affects the age. So length is millimeters, let's say measured in millimeters, and age is, let's say, some I think it's months here, I'm not sure, but let's say years things. So this whole thing is the whole data set is from a lake in Minnesota in the US. So it's like a lake in Minnesota, USA. That's the data set, and it's like the timeline like one. So and the age data you will see very clearly is from only 5 to 7, so 7 or less than equal to 7. So that's the data set they used, and the data was for some department data set with this thing. So let's try and do the data set. Let's try and see how we can do this. So now let's go, instead of doing this ggplot like this, let's do a small. Now you can get it up, right? You can just do this way, and then let's do a let's not do a geom smooth. Let's just do a without geom smooth. Let's just look at the just the data set, right? So listen. So you can see the data set like this, right? It's like, so 1 year old people have this much length, 2-year-old fish this much length, and so on and so forth. So it's clearly, I mean, you can't sort of. It's like this. It's like the way when we split up the other one, that is the heights one. We had these several things like that, right? So fish scales have like sort of annual ring like these, and these can be counted to determine the range of the fish. That's how count the age of the fish. So let me write down how they compute the age. Down. So how they compute the age of the fish is that fishes have this annual ring like trees. So fish have annual ring like trees. Right, and these can be used to count these can be used to compute the age. These are used to compute the age. So you compute the age. Compute the age, right? And length, of course, you just so now can you look at the number of rings and then say the age? So one can now go and do this Linear regression right here, do a, and then so let's say do the line and this, so you get this line. So you get a linear line because you do a least square regression line, you will get a linear line because you will drop a line in the middle of the data set, and that's your best possible line. But clearly you can see that it's not quite linear because there's a range in every point, right? So be careful. So I guess at this end it's okay, but this end is sort of very sort of not so. So you cannot use this linear regression to predict the so one should come up with a mechanism by which to say that, okay, linear model is not so correct. So one can easily observe from the graph. So what's the observation from the graph is that you cannot use the line to predict age from length. And that's something we can sort of observe from this thing, right? Okay, let's look at the next one, the next data set that we have. Let's see what the data set looks like. The next set is called the snow data set. So that's like predicting the weather. Happens here is a little more right for you, so you can sort of the next data set is predicting the weather. So what they want to do here is that so there's snowfall in September to December 31st, right? So can you use that? Can you use early season snowfall to predict what happens in January to June? So let's say you have September to December snowfall. Can you use that to predict the snowfall in, let's say, Jan to, let's say, June? Can you do that? That's the idea. You want to do that. That's what this is what one should do, right, to do this. So that's what this snow data set does. Let's go to snow data set. Let's go. What you do is you look at this. Let's see the snow data set. So you do snow data. That's the one that you have, and then this one tells you that. Let's say. So here to change the name to snow for you in your code. I've left it as this one old name, but yeah. So here, if you do head of snow underscore data, what you get is you get early and late. So how much was in the September December period, and how much was late period. So that's what we get here, right? Let's just go ahead and plot it again, and let's do the same thing, and then what do we get? So you get all over the place, right? There's really this is a plot for 93 years from 992. So 3 years data is there. And again, the line is something you get a line, you get a least regression line, but that's sort of the blue line is the best fit line. But I mean, it's anybody's guess if it's a good line or not. And somebody had a comment about that the correlation could be used. You could clearly see there's no sort of correlation in some sense. It's like sort of all over the place and so on. That's one. So then so let me go back to this thing. So there's sort of so it seems like the punchline is that seem like early and late are not related. Right. That's one thing. So last thing I want to sort of play with this is the last data set, and then go back to the first one we start off with. This is called turkey growth. So in this data set, what people do is they grew turkey, and it's a common experiment, and then they fed some with amino acids. Amino acids were fed to some. And then what you do is you try to see how does this affect the growth rate of that. So if the expected at dose equal to 0, the turkeys grew in some way, and then see what happens. Let's go here. Turkey data set. Let's go here. Come here. Go to data. Turkey underscore data. Let's look at this. Let's see how it looks like. So you have this. You have the gain and the amino acid given, and that's what this. So at dose equal to 0, there were 10 turkeys, and the average response of 5 pens of turkeys, and so on and so forth is given this thing. So let's try and plot this data set a little bit, see how it looks like. Again, it's sort of you can draw a line if you want, but again, it's not so clear how the line will be on. Because see, what the graph does is, except at dose equal to 0, where everybody matched up, right? The other, at each positive dose, there are 3 points, right? So what are 3 points? The 3 points are 3 sources of this methionine 9. That's an amino acid you give. So the variation points are at a given dosage. So between the sources, at dose equal to 0, a point arbitrarily in the graph. Since dose equal to means same for sources, nothing happens. Otherwise, dose. So now weight gain seems to sort of weight. If you look at the weight gain versus the amount of personal diet, the 3 symbols of points refer to 3 different sources of this methionine in some sense. That's what's going on. But again, the increase does not appear to be linear because it sort of goes up and down. If you look at the triangle, it starts here, it goes here, and then goes like this. So it sort of has a curve like this. It's not a linear curve. Right. So I won't do this Anscombe data set. I'll come back to the last one, this height data set, and conclude the class. So come back to the height one that you start off with. Then we can do this linear regression line, and then you get the fact that the whole thing is, oh, this is not the LM line. So let me do the LM line. Let me do the LM line. It's the regression line. Let me close that for today. That gives LM. So LM line is the middle line we found before in the previous method. And for the height data set, it seems linear. Of course, it's around the line. Of course, everybody's around the line. It's not clear if that's a good fit or a bad fit. And we discussed the other fit that we did, the loss fit, at some point in time, not today. Okay, I will stop for the day.